Microphone.
Yeah.
Oh, yeah, but you can't have it. It's mine. Sorry. Okay, you can have at least half of it. And the other part.
Okay, for the record, I'd like to wish David a very happy birthday. I'm sure we'll have more later. The work that I'm going to talk about appeared. I'm going to talk about soft theorems and symmetries in theories with magnetic monopoles and supersymmetry. And this was in a PRL 116, and also with supersymmetry with Dumitrisco, Mitra, and in 1511.07429. And there was also previous work was based on with Haidt, Porphyriadis, and KPEC. So before I get on to the new things that I want to talk about today, I have to briefly review some old things, and by that I mean a year or two, and that is that there's an infinite number of conserved charges in all electric conserved charges in all Abelian gauge theories. And so how do we see that? So I'm going to go through this a little bit quickly. Actually, I'm giving the Bekenstein lecture on Wednesday, and I will actually go through some of this a little bit more slowly then. And so we start with a theory with standard electromagnetic action, F squared plus matter. And then we have the standard electric charges, which we write in my normalization as the integral over a two-sphere of the star of the two-form field strength F. And of course, we can integrate by parts, use Gauss's law, and the constraints, and we can write that as the integral over a surface of which the two sphere is a boundary of the dual of the charged matter current. And we, of course, have gauge symmetry transformations. Delta A is d epsilon. And if we have a field of phi of charge q, we have E times qk times epsilon phi k with an I. And epsilon is identified mod 2 pi. Okay, so that's all standard. Now, important part of this story, these charges that I'm going to talk about are understood as conserved quantities with the property that if you know what they are, there's an infinite number of them, if you know what they are on the incoming, for the incoming scattering data, you know what they are on the outgoing scattering data. And so it's important to talk about null infinity, where a lot of the flux of these charges go. And in fact, the situation, the subject quite beautifully generalizes to the case of massive particles, which of course you would need to do for real QED. But I'm only going to discuss the simpler form of this story when there are only massless particles, except when I get to magnetic monopoles. But for now, let's just have only massless particles. So we have some scattering story of incoming and outgoing stuff, and some of it can be charged, massless charged particles, and we also have photons going in and out. And we have to study infinity rather carefully, and so we want to, when we're discussing future null infinity, scri plus, we have scri minus, we want to use so-called retarded coordinates. So u is retarded time. And for past null infinity, we want to use advanced coordinates. These would be the advanced, retarded, and then the advanced would be minus dv squared plus 2 dv dr plus r squared gamma zz bar dz bar, where gamma zz bar is just the round metric on the unit sphere. Now, as a matter of notational convenience, it takes a little bit of getting used to. When I use the retarded coordinates in the advanced coordinates, z means something different. They're antipodally related. So the z in the down here is antipodally related to the z up here. So if we have a light ray which crosses Minkowski space, it begins and ends at the same value of z. This is just a coordinate choice, but it makes all the formulas a lot simpler. And now I have to, it turns out that even in ordinary Maxwell electromagnetism, this point here where past and future null infinity meet is very singular. And I have to distinguish between what I call scri plus minus, the two-sphere at the boundary, lower boundary of future null infinity, from scri minus plus. And the reason for that is that even the ordinary Lienard-Vickert potential, 19th century, is singular there. And it turns out that the boundary condition that it obeys is that FZZ bar, or let's talk about this, FRV, the radial electric field, ZZ bar at scri plus minus is equal to FRU at scri minus plus with this antipodal identification. So the electric field here is not equal to the electric field down here. It's equal to the electric field over here. And I don't know how many of you knew this. I didn't know this 2 years ago. But if you go to Jackson and you take the formula for the Lienard-Vickert potential, that's what happens. And not only that, so the vector potential also obeys this antipodal relationship. AZ scri minus plus. And this is flat space-time. We draw, right, but drawing it that way, yeah, you know what I'm doing. Yeah, you're too sophisticated, Barack. So then it's, yeah. And it's easier to talk about the antipodal map. I couldn't have done this. I couldn't have said that the point here was related to the point there. Okay, and you can also see that this is the only possible Lorentz and CPT invariant boundary condition that you could impose. All right, so now one of the games that we're going to play is we're going to take things like AZ, which depend near scri plus, and we're going to do a kind of asymptotic analysis where we expand these AZ0 of U. We expand things, a kind of Pfefferman-Graham-like expansion, if you like. And so on. Okay, and that is what I meant by this matching. I should have written this equation first. It's only the leading components, the leading non-trivial components that are identified at null infinity. Okay, now it immediately follows that if we define q plus epsilon as equal to the integral over scribe plus minus epsilon star f, where epsilon is any smooth function on the two-sphere, since this is equal to that, it immediately follows that this is equal to q minus epsilon, which is at the integral over the top of scribe plus, the top of scribe minus of epsilon star f. Now, when epsilon is constant, so it's natural now to take these two expressions, to take this one and use the constraint and write it as an integral over scribe plus. So we can write this as an integral over scribe plus of d epsilon star f plus integral of scribe plus star j, and that will equal the same integral d epsilon star f plus the same integral over scribe minus. So epsilon, yeah, epsilon star j. So when epsilon is a constant, this formula just says that the sum of the incoming charges is equal to the sum of the outgoing charges. Very familiar formula. When epsilon is not a constant, it's equally true. It gives you an infinitely more conservation laws. It says that you take the incoming charges and you weight them by a function which depends on the angle on which they come in, an arbitrary function. And then you add in another term. What is this term? Well, this term, it's good to choose epsilon. This is true for any epsilon with the right boundary value, but it's good to choose epsilon to obey du epsilon equals 0 down here and dv epsilon equals 0 up here. And then this d epsilon is tangent to the sphere, so this looks like it's linear in the electromagnetic field. It's a transverse, it's contracted with a transverse polarization vector. So this is the zero mode of the transverse photon field. So when we get to the quantum theory, this will create a zero energy photon, otherwise known what I'll call as a soft photon, whose polarization is d epsilon. Okay, so now we have these conservation laws. There should also be some symmetries. Whenever you have conservation laws, you have symmetries. And indeed, you can do a canonical quantization of this theory, and you can show that the symmetries which this generates are q plus epsilon up on scribe plus, q plus epsilon az is just equal to I dz epsilon. So az depends on u, z, this is the leading component, z bar, and epsilon depends only on z and z bar. So this symmetry, the associated symmetries, and again, the epsilon is antipodally related. So the symmetry that is generated is one that it's a gauge transformation, but it's not a trivial one. It goes to an angle-dependent but time-independent constant on scribe plus, and function, and it goes to the antipodally related function on scribe minus. So these are large gauge transformations in, I guess I'll just give up on that. These are large gauge transformations in all Abelian gauge theories. And they could have, and indeed this was how I first got at them, they could have been discovered by a asymptotic symmetry analysis, which is a little bit less rigorous. The rules are not as clear. of the kind that Bondi, Metzner, Sachs did for general relativity in the 60s. And all you do is you say, okay, finiteness of the energy tells me that AZ should go like 1, AU should go like 1 over R, and AR should go like 1 over R squared for finiteness of energy. And the gauge transformations, which preserve these conditions, are delta A equals dz epsilon, and delta and with du epsilon equals 0. So these can be understood in the conventional way as asymptotic symmetry transformations. Okay, now when you have symmetries, you have a ward identity. So if we take a scattering amplitude, and let's just take any outstate whatsoever, we act on it with Q plus epsilon. S is the S matrix. And this should be equal to 0 for any outstate, for any instate, and for any function epsilon. So it sounds completely crazy that all all theories with abelian symmetries would have an infinite number of relationships among their S matrix elements, except for the fact that this very identity has been known in a wildly different presentation for 80 years now, or whoever you want, Bloch and Nordzig, Lowe, Weinberg, whatever. This turns out, after you do a lot of rewriting from this Scri plus basis to plane wave basis, after 3 or 4 pages, this turns out to be just completely equivalent to the Weinberg-Soft photon theorem. And this makes this discussion even stronger, because really my discussion here was classical, and we might be wondering about quantum effects and so on. And this is so this is sort of the lightning review of the previous stuff. But now we'd like to so the Weinberg-Soft theorem is known to be correct, has been proven to all orders in perturbation theory. So the Soft theorem is completely equivalent to the symmetries. And so we know that this is true in the quantum theory. But now, okay, so now I get on to some of the new things. So now we'd like to ask the question, in fact, I don't know if Nadi's here, but he was the first one who was asking me this. Are these symmetries, are these exact non-perturbative symmetries of electrodynamic theories? Well, in order to have a non-perturbative symmetry, you have to have a non-perturbative theory. So it makes no sense to ask whether this is an exact symmetry in QED, because QED doesn't exist. And as far as I know, maybe somebody has a counterexample at this conference, but as far as I know, all abelian theories that are exact have magnetic monopoles in some form or another. And if you have magnetic monopoles, so the traditional form of writing this is, the diagrammatic way of writing it is you write out with an insertion. So this Q epsilon plus, it's an operator. So there's a term in here in which you're inserting a soft photon. This is a soft photon. It's integrated over all time without any e to the I omega u. There's some kind of soft photon insertion is equal to some soft factor times the same S matrix element. I'll write down this soft factor in a second. The same S matrix element without the extra soft photon. Now, suppose there's magnetic monopoles in the theory. So the way that this soft factor is understood is you say, okay, I've got my scattering amplitude. It's actually a very simple argument. I've got a bunch of stuff coming in, a bunch of stuff going out. And now, let's say this is a charged particle. I add a little soft photon here. And then I have to do LAC reduction. I don't put these propagators on. But I have this propagator here, which had been truncated because before I added the soft photon, this was an external line. And working out, multiplying this vertex here by this propagator, which gives a pole because it's almost on shell, gives a collinear pole, becomes on shell when it's collinear if these are massless particles. So that's how you get this soft factor. Now, it's completely clear, in a theory with magnetic monopoles, you have to allow magnetic monopoles as asymptotic states. So there must be contributions to this, because you could still take a magnetic monopole, couple a soft photon, move its momentum only by a small amount, and you're going to get some kind of pole there. So it's completely clear that there must be corrections from magnetic monopoles. And so let me write down what this soft factor is. I'll write it here. The soft factor is the sum over all outgoing particles. What you get from this, the sum over all outgoing particles, the charge EK of the particle, the momentum PK dotted into the polarization of the photon, divided by the momentum, so this is the momentum of the soft photon, polarization epsilon, and this has momentum pk. So we have Q, the inner product of Q with pk. Picked a bad place to write that. And then you have minus the same thing with all the incoming particles. So clearly, this has to be corrected by some terms involving magnetic monopoles. Well, this is a simple exercise to figure out how to do this. The way we do it is we do a duality transformation. Now, I'm not assuming that this theory has a duality symmetry. I'm just going to rewrite it in terms of magnetic variables because this coupling is complicated in terms of the electric variables. But I'm just going to do a field redefinition. And the field redefinition, so we have monopoles now, whose charges are GK 1 over E, the integral of F. And so we define in the usual way, F dual is minus 4 pi over E squared, the Hodge dual of the usual F. E dual is, the dual coupling is 4 pi over E. And the dual electric charges are equal to the 1 over E dual, the dual of the new field, the old formula and the new variables. And when you plug all this in, you find that that's just equal to the new electric charges are the old magnetic charges, and the new magnetic charges are minus the new electric charges. And of course, F is equal to dA, but we also want to, and for a photon, A will be a polarization vector, epsilon alpha, one-form polarization vector, times e to the iqx. That'll be the wave function for A. But F tilde is dA tilde, which is equal to minus 4 pi over E squared star dA. And we want that to be equal to A tilde. That implies that A tilde is equal to epsilon tilde alpha e to the I q dot x. Okay, so this formula determines epsilon only up to a multiple of q. Once you know F, you know A, if you know the momentum, given the momentum, you know A is something like this, only up to a multiple of q. But one of the beautiful things about the soft theorem, and in fact this is a way that you can determine the soft theorem, is that if you shift, it doesn't matter which epsilon you use, because if you shift epsilon by q, these guys cancel, and you get the sum of the outgoing electric charges is equal to the sum of the incoming electric charges. So the soft variant factor is invariant, as it had better be, under such shifts of q. Okay, but now A dual couples to magnetic monopoles just by the same way that A coupled to electric charges. So we've basically done here. We don't have to even go through the diagrams because they're exactly the same. We've reduced it to the previous case. So what we get is a correction up here, the magnetic charge, and then we get pk dot the dual polarization, and then minus the same thing in. And again, we see that if we shift the dual polarization, which is magnetic gauge symmetry of the magnetic potential, then this thing is again invariant now by conservation of magnetic charge. So we now have a second infinity of conserved charges. I've written the first one here. But the second infinity, which already follows from the boundary conditions that I wrote here, is that q tilde plus is equal to the integral over scribe plus minus of f times any function epsilon tilde, and that's equal to q tilde minus, call it epsilon, which is equal to epsilon times any function of f over scribe plus, scribe minus, scribe minus plus. Okay, so there's a second infinity of conserved charges in addition to the first one. Now, this means it's interesting to note that if we look at FUZ, under duality, FUZ is equal to minus I e squared over 4 pi F tilde UZ. So under the electromagnetic duality transformations, the radiative modes at null infinity, it's a local transformation. They just get multiplied by I. And that's the fact that, electromagnetic waves are oscillating E and B, and you multiply by I, and you're just turning E into B. So if we integrate both these equations and drop the integration constant, we get AZ is equal to minus I e squared over 4 pi A tilde Z. So that means that magnetic gauge transformations which act on A tilde Z, if we try to understand them in terms of AZ, they look like complex gauge transformations. So adding in the magnetic part, the magnetic symmetry, complexifies the large gauge. It can be simply understood as having complexified the gauge group at infinity. And there's another way of understanding this complexification. If we compute the zero mode, the soft photon zero mode minus infinity du of FUZ, the soft photon mode, which is equal to A0 at scribe plus minus A minus A, the difference in the gauge potential at scribe plus plus and scribe plus minus, you can use the, let's call this NZ. This is one of the zero modes. This is a spontaneously broken symmetry, but this is invariant. F is invariant under the symmetry, but this zero mode N is the symplectic partner of the Goldstone boson. So the constant part of A, the sum of these two terms, would be the Goldstone boson. And N and its partner, in the electric case, you can use the Bianchi identity to show that N is the gradient of a real function, assuming that if there are no magnetic monopoles around, then the magnetic field must vanish at the boundaries. And that gives you some identities which imply that N is real. So the Goldstone boson on that, in that case, when we're only talking about the electric symmetries, yes? Changing the what? Let me finish what I was going to say here and then tell you that I don't know the answer to your question. So what I'm going to say here, what? What I'm going to say here is that when you assume there are no magnetic monopoles, the soft photon is the gradient of a real function. And there's a relationship, if there's no magnetic monopoles, there's a relationship between positively and negatively polarized soft photons, a non-local relationship on the sphere. And there's really only one Goldstone boson. When you don't have that, this becomes complex. So the clearest statement that I can make is that there's twice as many Goldstone bosons and there's and Z's. Now, to tell you why I can't answer your second question is, so this is something new in the subject of asymptotic symmetries, and it's going to get even a little weird in the sense that the usual thing is you start with some gauge group and you look at the non-trivial elements of that gauge group, and that's your asymptotic symmetry group. If you start with the electric gauge group, you miss the magnetic symmetries. If you start with the magnetic symmetries, you miss the electric symmetries. So you don't get everything that way. That's a too limited way of thinking about asymptotic symmetry groups, and after all, we all are used to the fact that how we write local redundant symmetries is kind of arbitrary. So they might or might not appear in any given 5 minutes. Jesus. Okay, wait a second. Wait, Kurt went 5 minutes. Wait.
Well, we want to leave time for questions.
We want to leave time for questions. Okay. All right. So I think I'm not going to get to the supersymmetry story, but I'm going to say one thing about it. Now, but in this case, when we have both magnetic and electric, we want to describe them both. It's rather tricky, and we have not. We're working on it now, but we have not understood how to construct the symplectic form and the commutators and to sort of give a really detailed answer to your question. But I hope that there is one, but it might not be in terms of, the original electric or magnetic. And also an interesting thing to do is to add a theta term, because these are boundary modes. They live at the boundary of scry. If you add a theta term, you get a Chern-Simon term at null infinity, and its boundaries at scry plus minus, you have dynamics there, and that will modify and mix the dynamics of these modes. So I think there's a very pretty story there, which we haven't yet worked out. And also, I think that there's a lot of interest in theories in which there are duality, non-trivial duality symmetries. This is true in any theory. But when there are non-trivial duality symmetries, these charges have to transform, and the soft factors and theorems have to transform in some nice way. Zohar, you keep. No, you won't get it. This argument doesn't happen. There's no antipodal identification in anti-de Sitter space. Anti-de Sitter space is very different. I don't think you get infinite dimensional symmetry groups in anti-de Sitter space except in ADS3 because there's a gap. This is all coming from the soft stuff. Let me just say what the result is with supersymmetry. So another question that we asked, maybe I'll write down one formula. Let's do the simplest kind of supersymmetry. Let's have n equals 1 supersymmetry. And then we know there's a soft Photino theorem. And it's pretty clear by now that whenever you have a soft theorem, you have a symmetry. And it may be some work to figure out what the symmetry is. But there's a soft Photino theorem. And so there's a symmetry. And not only is there a symmetry, but for the same reason that there's an infinite number of symmetries here, there will be an infinite number of symmetries in the case of the soft Photino. Now that sounds really strange because we're used to thinking of, n equals 1 QED as a theory with 4 fermionic symmetries. But in fact, the soft Photino theorem shows that there are infinitely many fermionic symmetries, and there are no way that they can be the subgroup of the usual supersymmetries. But in fact, they're there. It might be they're there. You might think that there might be some off-shell presentation of the theory in which these symmetries they act on the Photino by the Photino lambda gets a shift by dz chi, where chi is any function on any spinor on the sphere. They're kind of like a super partner of gauge transformations. And the algebra of these charges, f of chi, if you do a supersymmetry transformation of them by some parameter zeta alpha d alpha f of chi, you get back these charges, q, with epsilon equal to chi dot zeta. But it squares to 0 because supersymmetry commutes with gauge transformations. So that is that is the algebra. And so in that case, while there are infinitely many symmetries, we need, of course, to extend to n equals 4 and so on. We're not quite sure what the structure is going to be there, but again, it's pretty clear that there's going to be a lot of new symmetries in the n equals 4. So let me stop there for questions. Yes. Okay. The answer is yes, I do expect it, because physics is good and life is fun, and it will be fun to have such things. And I don't, so there is a question of which we did not run to in any of these examples of what you do. Some of the soft theorems have anomalies, and probably the best, here I just talked about leading soft theorems. There are also symmetries associated with subleading soft theorems and sub-subleading soft theorems, and those have anomalies in them. The best one with an anomaly, probably the simplest one to study, is if we had done this in classical non-Abelian gauge theory. The leading soft theorem already has an anomaly. Some of my postdocs are working on it. They think that the anomaly may be, this can all be understood as a current algebra. So in the electric case, the soft photon insertion is like, if you think of the sphere at infinity, if you think of the S matrix as defined on the conformal sphere at null infinity, the soft photon acts like the insertion of a 0-1 current, and it generates a U1 Kac-Moody algebra. In the non-Abelian gauge theory, we get a non-Abelian Kac-Moody algebra, and some people think that the anomaly means that there's a non-zero level in that algebra. I don't know. You know, many things could happen. Right. Yes. I'll bet you. Yeah. Anti-de Sitter is very different, and I think one of the exciting things about this, of course, we live, quantum field theory that we describe are in Minkowski space. It's the world that we live in, and the statements I'm making are statements about, in case anybody forgot. And I think it's fascinating that many of the structures, including the fundamental symmetries, that are really important for understanding these physics, are not present in anti-de Sitter space. So there are many things to learn about Minkowski space. We've learned a lot from anti-de Sitter space, but maybe there are many things to learn that we can't learn from anti-de Sitter space. We didn't know we were living in an expanding universe, and the experiments that we do, you know, the LHC doesn't use the fact that we're in an expanding universe. But of course, there should be, in an expanding universe, of course, there are soft cosmological soft theorems, and there may be a story more like this in de Sitter space than in anti-de Sitter space.
So I will ask you a question. Just to clarify the issue, let's assume I'm an experimenter. So what you generalize Weinberg's theorem to, let's say, emission of photons by dyne, right? Electrodynamics is
Yeah.
like particles, electrodynamics. So
Yeah.
you have a dyne, it emits very soft photons.
Yes.
Let's say I'm very good at measuring cross sections, including cross sections with soft photons. I have my detector, which is built of normal matter. It has all the electrons, and the only dyne I have, I brought some from somewhere. It is very heavy, and it's hard. It's impossible to produce many of them. So I know very well what is the polarization of an electric soft photon, because that's what I measure. Is it circular or linear? I can measure that. I cannot measure the polarizations of it. What is a dual photon if I have a...
Oh, you don't need to measure. You don't need to measure the dual photon.
But you have
No.
What was your
Generalizing the Weinberg? I used the dual photon as a trick to avoid the long work of understanding how ordinary photons cut. But after I was done with that trick, I wrote it. So I wrote the formula was S0 is equal to the sum of pk dot q, and then I had q dot ek e alpha plus gk e tilde alpha. So these are both related to the same photon, but essentially, if I go, I mean, you could very explicit formulas for it in our paper, but roughly speaking, if we have the orthogonal plane ZZ bar to be the orthogonal plane to the direction of propagation of the photon, then epsilon tilde z is just equal to I times epsilon z. It's just a factor of I. It's just a phase rotation by I. So this is a very explicit formula.
The magnetic charge is very large when the electric charge is small, right?
Well, that depends on the theory. I would assume so. That would be the usual case, yeah.
So
Wait, the magnetic charge, when the coupling is weak, yeah, G is small.
E
When
is
the
small is in our world,
Right.
G is large.
G, in our world, E is small as G is large. Though I'm conjecturing that this formula is non-perturbatively exact, and that it makes sense even when E and G are the same order.
So we can get